I was sitting in seat 14A the other day, just staring out at the wing, watching the world go by at 35,000 feet.
Oh, window seat fan, I see.
Oh, absolutely. Always. And it was perfectly smooth. The engines were just this steady hum. And I had this, well, I guess a very comforting but probably naive visualization of what was happening up front in the cockpit.
Let me guess. The classic aviator look.
Right, exactly. I pictured the pilot, hands gently resting on the yoke, eyes scanning the horizon, making these constant micro adjustments to keep us on that perfect line.
It is a very romantic image, very golden age of aviation. And honestly, for you as a passenger, that is exactly the feeling you want to have.
It is. But then I start digging into this stack of technical manuals and system descriptions you sent over for today's deep dive, and my entire image was totally shattered.
Shattered how? What stood out?
It feels less like driving a vintage sports car and more like programming a VCR while it's...
Well, it's hurtling through the air at 500 miles an hour.
Exactly. It's so technical.
That is surprisingly accurate. And honestly, if you are a new pilot or a trainee just stepping into your first jet simulator, that is the reality shock you have to get over. It's a huge hurdle.
So that is exactly who we're talking to today. If you are training to fly these things, or if you're just an aviation geek who wants to know how the magic trick actually works, this deep dive is for you.
We are getting into the weeds today.
We really are. We're looking at automated flight management, the invisible hand that actually flies the plane, the logic, the lines, and the weirdly specific rules that dictate how modern jetliners move. We'll be covering LNAV, VNAV, and the brain behind it all.
And the goal here isn't just to throw acronyms at you. We want to understand the personality of the machine. Because understanding how the computer thinks, how it translates a route into the physical movement of the ailerons and elevators, that is what keeps you ahead of the airplane.
So let's meet the brain. In the source materials, it's constantly referred to as the FMS, the Flight Management System.
Correct. Think of the FMS as the conductor. If you imagine the aircraft systems as an orchestra, so the engines, the navigation radios, the autopilot servos, FMS doesn't actually play the instruments itself.
It just holds the sheet music.
Exactly. It holds the sheet music. It digests a massive amount of data. It looks at navigation databases, GPS signals, inertial data from the plane's movement, and aerodynamic performance charts.
So it's the strategist. It decides where we need to be.
Right. It calculates the plan, and then it sends commands to the doers. It tells the flight control computers, which you know as the autopilot, where to point the nose, and it tells the autothrottle servos how much gas to give. It's a closed loop. The FMS thinks, the autopilot drives.
Okay, let's break this down the way the manuals do. We have two main axes of flight. We have the horizontal, which is LNAV, and the vertical, VNAV. Let's start with the horizontal. LNAV, lateral navigation.
In its simplest form, LNAV is the line on the map.
See, that sounds simple. I think of the GPS in my car. It highlights a route. I turn the steering wheel to follow it. But in a plane, LNAV is actually turning the wheel for you, right?
It is. But unlike your car, which is stuck on a physical road, a plane is in an open void. LNAV controls the 2D ground track. It guides the aircraft along an active route made up of legs. Every leg has a from waypoint and a to waypoint.
But here's the thing that jumped out at me in the Boeing manuals. It's not as simple as just being on the line. There's a whole logic to when the computer decides to grab that line.
Oh yeah, you can't just press the button anytime and expect it to work.
Right, and that seems like a classic trap for trainees. You're in the simulator, you press LNAV, and nothing happens.
The light doesn't come on, or it arms, but it doesn't turn.
Because of where you are in the sky.
Exactly. It's about engagement logic.
Right.
Let's use the Boeing architecture as our baseline here. To engage LNAV, the computer needs an active flight plan, obviously. But it also has a positional requirement. It's often called the 2.5-mile rule.
2.5.
Right. If you are on the runway or just took off, specifically above 50 feet radio altitude, LNAV will engage immediately if you are within 2.5 nautical miles of the active route leg.
So if you're close enough, it snaps to the grid.
Immediately. It takes command. But let's say air traffic control gave you a vector. They told you to fly heading 090 to avoid some traffic, and now you've drifted 5 miles away from that magenta line on your screen. You are outside the buffer.
So if I press the LNAV button now, does the plane bank hard to get back to the line?
No, and that's a built-in safety feature. If you press LNAV while you're 5 miles off course, the system logic changes. It doesn't engage, it arms. You'll see LNAV light up in white. which basically means waiting.
It's waiting for me.
It is waiting for you to fly the plane toward the line. The computer is essentially saying, I see the line, but I'm not going to jerk the wheel to get there. You point us toward it, and once I calculate that we are on a smooth intercept course, then I'll take over.
That is a really important distinction for a new pilot. It's not a save me button. It's a takeover once I've done the heavy lifting button.
Precisely. You have to assist the automation to help you. It turns green, meaning engaged, only when it knows it can capture the path smoothly.
Now, speaking of the computer doing the work, I found this edge case in the notes hilarious.
Right.
We always assume there's another waypoint, like the route just goes on forever. But what happens if you run out of dots?
The end of route scenario.
Yeah.
It happens more than you'd think, usually during complex arrivals where maybe you haven't sequenced the approach correctly in the computer.
So the plane hits the last waypoint. What does it do? Does it circle? Does it turn back to the airport?
Neither. LNAV stays engaged, but it defaults to a very basic logic. It just maintains the last known heading.
It just flies straight into the void.
Straight ahead. Until it runs out of fuel. It becomes a very expensive heading hold mode. It won't navigate you to safety, it just maintains the status quo. The computer has finished its task list, so it effectively says, I have no further instructions, I will proceed as is.
That is chillingly bureaucratic. Just not my job, not my problem.
It really is. That's why we always tell students, never run out of route. Always know what your active waypoint is.
Okay, so that's the left and right. That's the lines on the map. Now let's move to where the real magic, and honestly the real confusion happens. The vertical. VNAV.
Vertical navigation.
Reading through this, VNAV feels exponentially more complex than LNAV.
That's
LNAV is 2D chess. VNAV is 3D chess played in a wind tunnel.
That's a very fair assessment. LNAV only cares about where you are laterally. VNAV has to manage two variables simultaneously that are often fighting each other. The path, meaning your altitude, and your speed.
And it's not just doing this to keep the plane in the air. The notes mention that VNAV is essentially an economic tool.
That is its primary purpose in airline operations. The FMS calculates the most economical vertical profile. It looks at the gross weight of the plane, the wind at different altitudes, the temperature, and something called the cost index.
The cost index. That sounds like something the airline accountant types into the plane.
It practically is. It's a ratio of the cost of fuel versus the cost of time. If fuel is expensive, you put in a low cost index, and the plane flies slower and climbs differently to save gas.
And if you're running late?
If you're running late and time is money, you crank up the cost index, and VNAV commands a much more aggressive, faster profile.
So the computer is constantly balancing the checkbook while flying the plane.
Constantly. It's basically a flying accountant.
Let's talk about the climb, because there's a detail here that I think visually explains this perfectly for you. You're a new pilot. You engage VNAV for the climb. You look at the mode control panel, the dashboard where you usually dial in your speed, and the speed window goes blank.
It goes completely dark.
That would freak me out.
It's definitely startling the first time you see it in the sim, but that blank window is the computer telling you, I have the ball. You are no longer voting on the speed. The FMS is dictating it based on that cost index we talked about.
But here is the mechanics question. To go up, you need power and you need to point the nose up. Who is controlling what?
In a VNAV climb, we use a logic called pitch on speed. The auto throttle is told to set the engines to a fixed limit, usually maximum climb thrust. It just sets the power and leaves it there, roaring away.
So the throttle is dumb. It's just saying, go fast.
Exactly. It's pinned.
Yeah.
So who controls the airspeed? The elevators. The autopilot pitches the nose up or down to maintain the target speed.
Wait, walk me through that. If the plane is too slow?
It lowers the nose. Gravity helps you speed up.
And if it's too fast?
It raises the nose. You trade that extra kinetic energy for altitude. It's a constant trade-off. It's using the nose of the plane as the accelerator and brake, effectively.
That makes total sense. But planes don't just climb forever. Eventually, ATC comes on and says, level off at 10,000 feet.
And this is where the baton pass happens. As the aircraft approaches 10,000 feet, the logic has to flip. The autopilot obviously has to pitch down to fly level. It can no longer use pitch to control speed because pitch is now busy keeping us exactly at 10,000 feet.
So the throttle has to wake up.
The auto throttle wakes up and switches duties. It moves from fixed power to speed mode. Now, the throttle modulates to hold the speed and the pitch holds the altitude.
It's a dance. You're constantly swapping who is leading, the throttle or the yoke.
And knowing who is leading at any given moment is what separates a button pusher from a true system manager. That is the #1 thing I look for when I'm observing a check ride. Does the pilot know who is driving?
Okay, let's go to the other side of the mountain. The descent. This is where I feel like the invisible hand is really doing some heavy calculus.
Calculus is the right word. In fact, to plan a descent, the FMS does the math backwards. It starts from where you want to land, or specifically the final approach fix, and calculates backwards and upwards all the way to your cruise altitude.
To find the perfect top of descent, TD.
The TD point. And here is the critical assumption the computer makes. It assumes an idle thrust descent. It wants to pull the throttles back to absolute zero and glide down a perfect geometric path to the runway.
Because engines at idle burn the least fuel.
Correct. It's the most efficient way to fly. Gravity is free.
But the real world is messy. We have wind, and this section of the notes gave me a real aha moment regarding the physics. It explains how the autopilot handles wind without the pilot touching anything.
This is pure physics in action, and it's where VNAV gets really tricky.
Let's run the scenarios. Scenario A, you have a headwind. You're gliding down this invisible VNAV path. Engines are at idle, but the wind is hitting you in the face. It's slowing your ground speed.
Right, so you aren't covering enough distance across the ground for the altitude you're losing. You start dropping below the calculated path. You're getting too low.
So the FMS sees this happening. What does it do?
It pitches the nose up. It tries to shallow the descent to get back up to the line. But basic physics, when you pitch up without adding power, what happens?
You lose speed. You could stall.
Exactly. You bleed off airspeed. The FMS sees this happening, and since it won't let you fall out of the sky, the auto throttle has to wake up. It adds power to maintain the target airspeed.
So in a headwind, the perfect idle descent is ruined. We have to burn gas to stay on the line.
It's not ideal for the wallet, but it's safe. It keeps you on the vertical path.
Now flip it. Scenario B, a tailwind. The wind is pushing you from behind. You are flying fast across the ground.
Now the plane is being pushed above the calculated path. You are too high. To catch the path, the FMS pitches the nose down. It dives.
But diving makes you go faster.
Correct. It increases acceleration. Now remember our climb logic. In a descent, the engines are usually already at idle. They can't produce less than zero thrust. The computer has no way to slow down using the engines.
It's out of options. It's diving to catch the path, picking up speed.
It's risking an overspeed. It's pushing the limits of the airframe or the flaps. And this is where the computer finally turns to the human and admits defeat. It triggers a message on the screen. Drag required.
That's the airplane saying, help me.
It's saying, I've done the math and the physics don't work unless you add drag. That's when you, the pilot, have to reach over and deploy the speed brakes.
I love that distinction. In a headwind, the plane fixes it by adding gas. In a tailwind, the plane speeds up till it effectively yells at you to pull the handbrake.
And for a new pilot, anticipating that tailwind descent is vital. If you know you have a 50-knot tailwind, don't wait for the message. Be ready to manage the energy before the computer panics.
It's proactive versus reactive.
Always be proactive.
Now, we've been using a lot of Boeing-style terminology here, LNAV, VNAV, but I want to shift gears to the other giant in the sky, Airbus, because their fly-by-wire architecture handles this slightly differently. And your notes highlight a really specific trap for new pilots transitioning to the Airbus world.
It's a fundamental philosophy difference. Airbus uses the concepts of managed versus selected guidance. It's very tactical.
Push versus pull.
Right. On the Airbus flight control unit, the glare shield panel, the knobs can be pushed in or pulled out. The rule of thumb is, if you push the knob, you are giving control to the computer. You're telling it, fly what is in the FMS.
That's managed mode.
Yes. Managed NAV for lateral, managed climb or descent for vertical. The aircraft strictly follows the pre-computed trajectory. It respects every waypoint, every speed limit, every altitude constraint. It is the obedient servant of the flight plan.
But sometimes ATC tells you to turn. They say turn left, heading 090. So you grab the heading knob and you pull it toward you. That's selected mode.
You are selecting a specific value. You are taking over. But here's the critical link that creates the trap, and this is what bites new pilots constantly. Vertical follows lateral.
Vertical follows lateral. That sounds like a law of physics. What does it actually mean in practice?
It means the computer links your altitude behavior to your map position. In the Airbus logic, a vertical constraint like cross waypoint alpha at 10,000 feet is geographically tied to waypoint alpha.
Okay, that makes sense.
Now, imagine you are descending toward waypoint alpha in managed mode. The plane knows it needs to hit 10,000 feet there. It's planning for it. But suddenly you pull the heading knob to fly heading 090. You are now flying away from waypoint alpha.
I'm leaving the map. I'm breaking the lateral path.
Exactly. And because you have left the lateral path, the computer decides that the vertical constraints associated with that path are no longer valid.
So it just dumps the altitude restriction.
It automatically reverts the vertical mode. This is called mode reversion. It might switch from managed descent to something like open descent or vertical speed.
And open descent doesn't care about Waypoint Alpha's altitude rules.
No, it disregards them entirely. Because in the computer's mind, since you aren't flying to the waypoint, why should it respect the altitude for that waypoint?
That is a massive gotcha. You turn the heading knob, and suddenly the plane blows right through the altitude floor you thought was protected.
It is the source of many altitude deviations for new Airbus pilots. You turn off the route, and the safety net disappears.
So the lesson is, if you pull lateral, you have to watch vertical.
Always check your FMA, the flight mode annunciator. That little text at the top of the screen is the only way to know for sure what the plane is thinking. If you change one thing, verify what the other axis is doing.
It really all comes back to monitoring. We call it automation. But reading all this, it feels more like delegation. You're the manager. The FMS is the worker.
That's the perfect way to see it. And like any manager, you can't just walk out of the office and assume the worker is doing the right thing.
Especially if the worker is a computer that will blindly fly a heading until it runs out of fuel.
Exactly. It does what you tell it, not what you want it to do.
So for you listening, whether you're stepping into a simulator soon or you just want to know what's happening up front, what's the big takeaway here?
It's about the partnership. The FMS is brilliant at math. It can calculate fuel efficiency and top of descent points better than any human. That's the managed world. But it relies on you to understand the selected world, when to intervene.
And knowing the consequences of that intervention.
Knowing that pulling a heading knob might delete your altitude protection. Or knowing that a tailwind will force you to use speed brakes. The machine follows the math, but you have to understand the flight.
I want to go back to one thing you mentioned earlier, that drag-required message. It feels like a metaphor for this whole discussion.
How so?
Well, we talked about how the FMS is obsessed with efficiency. It wants that perfect idle thrust descent to save money. That's its primary goal.
Right. It's the accountant again.
But if the automation holds that efficient path so strictly that it ends up overspeeding, forcing you to throw out the speed brakes, aren't you just converting that expensive energy into noise and turbulence?
That is the ultimate irony. You're burning potential energy, which you paid for in fuel to climb up there, just to stay on a line that was mathematically calculated to save energy.
So at what point does strict adherence to the computer's path actually become less efficient than a human pilot simply looking out the window, feeling the tailwind, and starting the descent 5 miles early?
That is the million-dollar question for modern aviation. The computer knows the exact cost of fuel, but it doesn't always know the cost of complexity. Sometimes, the smartest computer in the cockpit is still the one wearing the headset.
The invisible hand is powerful, but it still needs a firm handshake from the human in the seat.
I couldn't have said it better myself.
Thanks for diving in with us. Keep an eye on your FMAs. We'll see you on the next deep dive.